Hey everyone, I'm Praveen and welcome to AI Sparks, where artificial intelligence meets innovation and excitement. On this channel, we spark curiosity and ignite imagination with AI powered insights, tutorials, and explorations. From machine learning to robotics, we'll dive into the future today. Imagine this: you're inside the mind of a large language model, not a chatbot window, not a prompt, but the thinking itself. At first, it looks like a straight road. Step 1, step 2, step 3, classic chain of thought. But suddenly, the road bends. It loops back on itself. It branches. It reconnects in places you didn't expect. And that's where the story begins. This paper is called The Molecular Structure of Thought, and the idea is surprisingly poetic. The authors ask a simple question: why do large language models struggle to learn long reasoning? Even when we show them examples, we give them step by step solutions, human written chains, distilled traces from weaker models, and still something breaks. The reasoning drifts, the logic collapses. The model forgets where it started. So the authors take a step back. What if reasoning isn't a chain at all? What if it's a molecule? Think about chemistry for a second. A molecule isn't just atoms lined up, it's bonds. Different kinds of bonds: strong ones, weak ones, flexible ones. Now map that idea onto reasoning. According to the paper, effective long chain of thought reasoning is held together by three bonds. First, deep reasoning. This is the backbone. Like a covalent bond, one step must justify the next. Break this bond, and everything downstream collapses. Second, self reflection. This is where things get interesting. Later steps loop back. They question earlier assumptions. They revise, correct, and fold the reasoning onto itself. Like hydrogen bonds in proteins, this is what gives thought its stability. And the third, self exploration. These are the weak tentative moves. What if this path works? Let's test an alternative. They're like van der Waals forces, individually weak, but crucial for connecting distant ideas. Together, these three bonds form a thinking molecule. Here's the twist: the authors show that models don't learn long reasoning by copying words, they learn the structure. You can replace reasoning keywords, you can remove phrases like let's think again, and the model still works as long as the bond structure stays intact. That's wild. It means the model isn't memorizing steps, it's internalizing a topology of thought. Now comes the problem: there isn't just one correct molecule. The paper introduces the idea of semantic isomers: same atoms, same concepts, different bond arrangements. Two reasoning traces can solve the same problem, yet train the model very differently. Some structures converge fast, others fight themselves. And here's a major pitfall: if you mix incompatible reasoning structures, even if both are good on their own, the model collapses into chaos. Performance drops, stability disappears. Reasoning molecules don't like being fused randomly. So, what do the authors do? They stop copying reasoning traces altogether. Instead, they propose MoldSyn, a method that doesn't transfer words but transfers behavior distributions. It learns how often models reflect, when they explore, how deep reasoning transitions happen. Then it synthesizes new chains from scratch with the same molecular shape. The result: stronger long reasoning, more stable reinforcement learning, and better performance across benchmarks. So, the takeaway: long chain of thought isn't a script, it's not a checklist, and it's definitely not just longer text. It's a folded structure, a molecule of thought held together by bonds. And once you see it that way, you start to wonder: if reasoning has a chemistry, what other hidden structures are still waiting to be discovered? If you found this helpful, hit like, subscribe, and comment which AI system you want to build next. Stay sparked. See you in the next video.